Good morning. Hope you guys are starting off your day wonderfully. We are going to continue talking about correlation today. So this is 3.4, and we are going to talk about a few of the really important properties of correlation. So first, we're going to start out with the formula. Now, before you guys freak out and go, yeah, I am not doing this, I want you to just hear me clearly. You will never have to do this formula by hand, okay? But I do want to talk to you about the parts of the formula, okay? So here's the formula for correlation right here, okay? So what that is it's the summation. That's what this little e right here is about, the summation of, and then this in parentheses, this first parenthesis right here. If you notice, it is the x value of a point minus the mean of the x values divided by the standard deviation of the x values. I don't know about you guys, but I think that sounds very much like a z-score. Value minus mean divided by standard deviation. And that's exactly what it is. So basically what you're doing here, so remember, you've got your scatter plot, right? And each of these dots has an x and a y value. You're standardizing the x value. You're getting the z-score for that particular x value. Then if you look to the next parenthesis, you'll see we take the y value and subtract the mean and divide by the standard deviation. So I'm getting the standard deviation, the standardized z-score for the y value for the point. And so really, if you look here, this is kind of the simplified version, is I'm getting the z-score for the x value, the z-score for the y value, and then what we do is we multiply them. So I get their products. Once I get every single point's product, okay, so this one's going to have its z-score for the x and z-score for the y, and I'm going to multiply them. And then this one's going to have it, and this one. So after I get every single one of those products, then I'm going to sum them up. That's what the summation sign is all about, okay? And then the final step of the formula is to divide by n minus 1, which is going to basically be like an average, okay? So that's how I get a correlation. I know that you guys do not care about that formula, okay? I know it. I'm not dumb. I was not born yesterday. I know you don't care about this formula, and you're like, you know what? I'm never going to use it, so what's the point? Here's the big thing to know. The correlation value, R, is made up of two z-scores that have been multiplied together and then added up with all the other products. So that means that correlation is a standardized value. Correlation is a standard value. And that's going to be very important as we look over some of the properties of correlation. Okay? So I just wanted to show you guys that formula and where all of these different properties are about to come from. All right, so some properties of correlation. Correlation makes no distinction between explanatory and response variables. What I mean by that is it makes no difference which variable you call x and which one you call y in regards to calculating the correlation. The correlation will be the same in either case. As you can see in the formula, reversing the roles of x and y would only change the order of the multiplication. The order of the multiplication, not the product. For example, let's say my x had a z-score of, 3, and my y had a z-score of 2. Well, what is 3 times 2? That equals 6. But let's say I had flipped my x and my y axis. Then I would have 2 times 3. And what's 2 times 3? Still 6. So it doesn't matter which one is x and which one is y in regards to the correlation. Also, let's look at the graph of if they were flipped. So the graph on the left has foot length on the x-axis and height on the y-axis. But on the right, we have flipped them. And we have height on the x-axis and foot length on the y-axis. If you look, you can kind of tell. Think about a line like the parent function. It's almost like this scatter plot just flipped around the parent function. Okay, so that's basically what we've done. All of these dots just basically flip around and go onto the other side of the parent function. But they're still correlated to each other in the same pattern. So if you look at the pattern of each of these, you can see it's the same pattern, okay? So like these two guys are right here, right? And then like these two here are right here. But again, the pattern's just flipped around that parent function. So again, just to reiterate, if I switch my x and y on accident, it's not going to make a difference for correlation. It will make a difference on whether or not you have the correct explanatory and response variable, though. Okay, so it is still important to make sure that you do it right, but that's just kind of something to keep in mind. All right, let's turn the page and see what else we can find out about correlation. So because R uses the standardized value of the observations, so these z-scores, that means that R does not change when we change units of measurement. So if I change units, R is not going to change. So what that means then is that if I change, like for example, this graph is in centimeters for foot length. So we have centimeters for our foot length. If I change that to inches, for example, then that's not going to change the distance of the dots to each other, okay? And so they're still going to be kind of correlated to each other. No matter if I'm using centimeters or inches, they're going to be correlated to each other in the same way, all right? So my standardized score doesn't change because their distance from the mean and the standard deviation hasn't changed. So I can change the units all day long. I can go from centimeters to inches to millimeters to whatever, and my R value will never change. So R is 0.84 over here, and it's still 0.84 when I change them to inches. Okay? That's kind of a cool thing. So I don't have to worry about R changing on me because it's a standardized value that that is not going to change just because we change the units. Okay? All right, the next thing that we're going to look at is the correlation R has no units. It does not have units at all. The reason is, again, it is a standardized value. It is a standardized value. So it does not matter if I am talking about inches or centimeters or whatever it might be. There is no units attached to the correlation value. Correlation is a standardized value that tells me strength and direction of the association. It has nothing to do with units. The units go away just like they went away with z-scores. Z-scores don't have units. R values don't have units. Okay? All right, let's look at an example. So the scatter plot shows the relationship between 40-yard dash times and long jump distances from less than 3.2. The correlation is negative 0.838. Okay, so just to kind of refresh your memory, that would be a negative and a strong association. Okay, what would happen to the correlation if long jump was plotted on the horizontal axis and dash time was plotted on the vertical axis? What would happen? I'll give you a second to think about that. All right, so what would happen if we switch the x and the y axis? What would happen to the correlation? Absolutely nothing. Very good. Nothing would happen. All right, so the correlation would still be negative 0.838 because the correlation makes no distinction between the explanatory and response variable. So what would happen to the correlation? It would stay the same. It would stay the same. Because correlation makes no distinction between x and y variables. Again, remember, this is because whether I do the x times the y or the y times the x, multiplication can be reversed and you get the same thing. Okay? All right, the next question says, what would happen to the correlation if long jump distance was measured in feet instead of inches? So what if we change the inches to feet? What's going to happen to the correlation? It's going to stay the same. Correlation is a standardized value and unit changes do not affect it. All right, so it would stay the same because correlation is not affected by unit changes. Okay, again, it's because it's a standardized value. Units don't matter to standardized values. All right, last question. Sabrine claims that the correlation between long jump distance and dash time is r equals negative 0.838 inches per second. Is this correct? Well, it kind of seems like she's partially right. It does literally say right there that r is negative 0.838, but she included units. We do not include units with r. R does not have units, all right? So the value is correct, but r does not have units. The value is correct, but r does not have units, okay? So for Sabrina, she got the correct number because it literally says it on the paper. The correlation does not have units, so including inches per second is not correct. All right, so to kind of summarize all of that one more time, correlation is a standardized value, and it will not change if you switch x and y. It does not change when you have unit changes, and correlation does not have units itself. It's a standardized value. All right, so now what we're going to do is we're going to talk about what happens when you have some outliers. So correlation is a good way to measure the strength and the direction of a linear relationship, but it does have some limitations. So remember, correlation does not reveal the form of the relationship. We have to actually see the scatter plot. Nor does it imply a cause and effect relationship. Remember all those relationships on that website yesterday? None of those things were causing each other to happen. They just happened to be correlated. So the following property is another limitation of the correlation. So again, the formula for correlation involves the mean, which is X bar and Y bar, and the standard deviation for both of the variables, okay? So the correlation includes the mean, which is X bar and Y bar, and the standard deviation, which is S sub X and S sub Y, for both of the variables. Back in chapter 1, we talked about the mean and the standard deviation as being not resistant, meaning that if I change extreme values, the mean and the standard deviation are also going to change. So the mean and the standard deviation are not resistant to outliers. So if I'm using the mean of X and the mean of Y and the standard deviation of X and the standard deviation of Y in my correlation formula, then we should not be surprised that the correlation is not resistant to outliers either. Okay, so let's consider a scatter plot where the majority of points form a positive linear association. So here's our example. An outlier that is in the same pattern as the rest of the points. So again, if you look at this dot that has just been added here, you'll see if I kind of visualize a line, it's pretty well in the linear pattern. That is going to make the correlation closer to 1, meaning it's going to make the correlation stronger, okay? And that's because now I have a dot that is in the linear pattern and kind of like saying, hey, this line is a really good linear fit. Look at this. It even works way out here. And so if the dot is in the general trend or the path of the linear association, then it is going to make the correlation stronger or closer to 1 or -1 if it was negative. Okay? Now, what if the dot is not in the pattern? That's going to make the correlation closer to 0 or possibly even negative. There are some correlations that if the dot is, really far out there and really far below the rest of the pattern, it can even take a positive correlation and turn it negative. And so this kind of an outlier is going to cause my data to get weaker. So my correlation would be weaker because it is further outside of the data that was originally there. Okay, so let's try an example. The scatter plot shows the relationship between the amount of saturated fat and the number of calories for 18 different granola bars. How does the point in the upper right corner affect the correlation? So we're talking about this guy right up here. How does that guy affect the correlation? So basically, look at the trend of the data. And do you think that dot is really far away from the rest of the data? Or is it kind of pretty close to the trend of the data? Meaning it would make it stronger or would it make it weaker? Okay, so let's think about that for a second. What's this dot going to do? So I would say that this data value is fairly close to the linear trend. And so I think that the correlation is going to be stronger due to that fact. Let's see what the official answer says. Okay, with the outlier, we have a correlation of 0.82. Without the outlier, when I take it out, the correlation is only 0.5. So that point caused the correlation to be stronger. Okay, so if we keep the dot, then the correlation would be stronger. If we take it away, the correlation gets weaker. Okay, so this point would weaken the correlation if removed, because it is in the trend of the data. This point would weaken the correlation if removed because it is in the trend of the data. So if I remove this point, it would weaken the correlation. And it only weakens it because it's in the trend of the data. All right, let's look at our example for today. All right, this, let's see, what is the name of this extinct beast? The Archaeopteryx, sure, is an extinct beast having feathers like a bird, but teeth and a long bony tail like a reptile. Because the known specimens differ greatly in size, some scientists think that they are different species rather than individuals from the same species. However, if the specimens belong to the same species and different in size because some are younger than others, there would be a positive linear relationship between the lengths of a pair of bones from these individuals. An outlier from this relationship would suggest a different species. Here are data on the lengths in centimeters of the femur, a leg bone, and the humerus, a bone in the upper arm, for 5 specimens that preserve both bones, along with the scatter plot. And the correlation is R equals 0.994. Very strong and positive. So we've got our scatter plot here. We've got our data. So based on this data, do you think that all 5 specimens come from the same species? So again, part of this paragraph that we just read says that an outlier from this relationship would suggest a different species. So basically, when you look at this scatter plot, do you see anything that would be considered an outlier? Probably not. So since all values are in a linear pattern, it appears all specimens are from the same species. So basically, since there's no outlier, it appears that we're okay. So it appears that all 5 specimens come from the same species, as there is a strong positive linear relationship between the lengths of femur bones and the length of humerus bones. So there's not really an outlier. So it looks like we've got a pretty strong association here. All right, number 2. Number 2 says, suppose that a new fossil was discovered. If the femur is 70 centimeters and the humerus is 40, do you think this specimen came from the same species? So the femur is 70 centimeters and the humerus is 40. So if I go to the femur of 70 and a humerus of 40, I would be right down here. Do you think that that would be the same species? Probably not, because of the fact that that is very far outside of the trend of the data, and so that would make me think that this would definitely not be from the same species. It would definitely be an outlier. So let's see what we've got here. It says, This point does not follow the strong linear trend, so this fossil is unlikely to be from the same species. Okay, so this point does not follow the trend, so this fossil is unlikely to be from this species. Awesome. And the last question, what effect will this new fossil have on the correlation? So what is this new fossil going to have on the correlation? Is the correlation going to get closer to 1 and stronger, or is it going to get closer to 0 and weaker? Because this new fossil does not fit in the linear pattern, it will make the correlation closer to 0. Wow, look at that. It goes from 0.99 to 0.51. That's really weak. Wow. All right, so this value would weaken the correlation because it is not in the linear pattern. All right, very good, guys. So now what you're going to do is you're going to work on your saplings. So you need to do 3.1 to 3.4. Okay, we've got, I'm going to let you guys work on it the rest of this period. So it looks like you should probably have about 20 minutes or so, maybe 15, 20 minutes. So you're going to work on sapling. And then tomorrow you'll get another day to work on 3.1 to 3.4. So no excuses to not have sapling done before Wednesday, which is when your quiz is. So we're going to take a quiz on Wednesday over 3.1 to 3.4. So you guys get to work. Thank you guys very much, and I will see you tomorrow.